Hi, in this video I want to share how I did sim-to-real transfer for a pendulum, inverted pendulum robot like this. So let's first look at the final product first. So here's the robot, and it balances on two legs. I can move it forward by clicking the corresponding button. I can turn it left, I can turn it right, and let's move it forward a little bit here. There we go. And turning left a little bit forward. So, and then we can also go backwards like this. And the robot is quite stable against perturbations. I can push it, I can collide it with objects, and it will still be okay. It's not going to fall over. So as you can see, we can also turn it around and make a collision from the front. And as you can see, it's quite smoothly balancing itself back towards a stable position. So even if I collide with myself, it will still be okay, like this. So here is the robot from the outside. It's got about 1.25 kilograms of mass attached to a rod, which is about 55 centimeters. And the axis of rotation is shown in this arrow. So basically two wheels and attached with a heavy mass on the top like this. And the reason why I have the mass on the top is to maximize inertia. Inertia is calculated as mass times the position of the mass from the axis of rotation. And this, if we have a high inertia, then that means the angular acceleration is low, and which means we will have a much easier time balancing the robot. And here is what the internals of the robot looks like. The robot is running a policy on Jetson Xavier NX mini PC here, and we can read the current gyroscope reading from an IMU unit, which is attached to the top plate. And the policy is outputting joint velocity actions to the two motors, and I have a RS485 connector connecting to the two motors here. So let's take a look at the robot model used for policy training. As you can see here, it's quite detailed, but not as detailed as you would expect. So here is the weight, the rod, and the wheels. And most of the parts were 3D printed. And if we look at the inside of the robot here, we can take a look at the parts here. So here we have the Jetson Xavier in the center, and we have this a bunch of wires. And we have a cable box and the IMU mount here, which is a small breadboard. And so we can take a look at how I modeled these. So here is the Xavier NX model here. The bunch of cables were modeled as simply a rectangular block here, and the breadboard mount and the wiring box here. So it's not as exact as you would expect, but I've measured each part on a scale, so the weight of each part is exactly correct, but some of the details are not missing. And I don't think it's going to matter so much, because most of the balancing is done only along the axis of rotation, and everything else is kind of an extra bit of information which we don't really need. So here we have the robot loaded into IsaacSim, and if we start the simulation, we can see it fall over kind of naturally. The first thing I did is I added a differential controller to the robot, and the reason is I wanted to test how the robot moves with applied torque. So first we need to remove stiffness, and we can start playing around with values of damping. That might, that might make sense here. So with the value of 1, it's a little, maybe a little strong. As you can see, it just flies off. But that's because the differential controller's scale is actually quite big, I believe. Yeah, so this is value of 6 means, I believe, 6 pi, which is a little too crazy. So let's set this to 2 and see how that looks. Yeah, so that looks kind of reasonable. Yep. I can't balance it myself, but hopefully the robot will learn how to do it. So this way I can kind of set an initial damping value, and then I can use that for my training. So here is my training setup. Here we have two actuators. This is the right actuator and this is the left actuator. They're not the same size, so I've set 2 different effort limits. I believe this is in Newton meters. And this is the damping value, and as I've explained, we want to set it to some reasonable value, and I'd rather train the policy at this damping and then tune the gain on the motor instead of training the policy with different damping values. The reason is the policy takes much longer to train, and setting a variable on the motor is much faster. So the other important thing here is, instead of using the simulation to calculate angular velocities and position of the robot, I've instead spawned an IMU unit on the robot itself. This is done by specifying an object prim to spawn the IMU on, and then I can set the position. And here I've decided that gravity has a negative value, which is the same as the IMU that's mounted on the robot. The robot is trained using joint velocity action, and the scaling factor is 6.28, in other words 2 pi, so as we saw in the Isaac sim. And the commands are for making the robot go forward or backwards, and also turning. So this is deciding the command values. So this is calculated based on the size of the wheel and the scaling factor. Anything more than this, the robot actually cannot physically reach because of the scaling factor here. As for observations, we have the simple one is the last action and joint velocity. These are the last action is very simple, and joint velocity is obtained from the motor, so the motor will tell us what the current joint velocity is. The velocity command is the commanded velocity from the command configuration, and on top of that I am using only 2 additional features. So forward velocity is the forward velocity of the robot, and that's calculated very simply as the radius of the wheel times the rotational speed of the 2 motors. So this is the rotational speed of the right motor and the rotational speed of the left motor. There is a negative sign here because the axis of rotation is opposite, but in reality this is the sum of these 2 values. So this is simply telling the robot how fast the robot is currently moving based on the size of the wheel and how fast the motors are spinning. And the other feature is the IMU feature. So the IMU is mounted on the robot, and you can access it in the call of this manager term using the asset configuration with the IMU, name of the IMU here. And here I've named it as IMU, so it's the name of this variable, not just IMU. And so here is the IMU, and I've added random noise. So my IMU has, when the IMU is not moving, it actually has quite a lot of noise. So I've collected stable data, and then I take the standard deviation in the acceleration term and the gyro term, and then I use that as kind of a noise for my IMU data. So from the IMU data, I can collect the gyroscope rotational velocities and then the acceleration. And then I calculate, and then I add some noise that's randomly sampled from a random distribution. With the, this part is collected from the real IMU. And then I calculate the current orientation pitch angle of the robot by using the forward vector and then the gravity vector. And then this is only based on the acceleration term. So if the robot is moving, then it might have a non-zero acceleration. So this one is not the actual pitch angle. So this one is calculating the actual pitch angle, and this is called a complementary filter. So basically it combines the gyroscope and then the time step, so how long we've been spinning at that angular velocity to calculate the current pitch angle. So the IMU feature is the gyroscope angular velocity is directly obtained from the IMU, and then the pitch angle, which is calculated using something called complementary filter. So the observation is actually quite simple, and here is my domain randomization. So the robot is actually spawned without any randomness in the pose or velocity. But here I am changing the position of the two joints. So so this really doesn't matter, because this is the current position of the robot, of the joint. So it's a wheel, so it really doesn't matter. But this is important because this is giving an initial velocity to the wheels when we reset the robot. Here I'm adding a random mass of minus 100 grams to plus 100 grams to the base plate, but the plate is actually the whole robot, so it's adding extra plus or minus 100 grams for the mass of the robot. Now this one is actually probably the most important domain randomization, which is the randomizing the center of mass. Now the robot can only move back and forth, so the y center of mass and the z center of mass is not that important, but the the forward direction center of mass is quite important. So I am changing the position of the center of mass between 2.5 centimeters plus or minus 2.5 centimeters here. And here we randomly change the PD value, stiffness value, the damping value of the joints by plus or minus 1.5 degrees. Here I have the reward terms. The reward terms, these are the velocity tracking, so forward, backwards, and this is the angular velocity tracking. Here I have the alive term, and here we have torque usage, penal regularizer, and joint acceleration regularizer. So as you can see, this is really, really simple reward tracking. And the termination is done if the robot's base touches the ground, in which case it will terminate. So let's take a look at how training progresses. So at time equal to, step 0, you can see it kind of just falls over and then resets like this. At step 5000, you can see it's already balancing well, but it can't track the requested command velocity. So at 20,000, it's much more confident in its motion. You can see the requested and the current position velocities kind of start to match nicely. And at step 6000 we have something like this, and at 75,000 step it's looking quite nice. Now this training usually takes about 30 minutes to train as the first step, and then once this is done I reduce the entropy and KL divergence terms, and then I finish off the training with the goal of minimizing the standard deviation noise for the policy. So the policy is now trained, and we can move on to the sim-to-real transfer. To do this, I've come up with this kind of structure. So the main loop here is running the policy at 50 Hertz, and into it is coming, we have three different data input coming into the main loop. The first one is the IMU data. The IMU is connected to the I2C pins on the Jetson, and this data is read by an IMU publisher program. This program takes the IMU data, it smooths it, and then publishes it again at 400 Hertz. And for this one I'm using a library called 0MQ. 0MQ is basically like ROS. It allows messaging, but it's much more lightweight. And also the Jetson Xavier I'm using is already reached its end of life, so there's no more modern ROS2 repository framework that I can install. Also, it's kind of heavy. This is a very lightweight, and it does exactly what I need, so I've decided to use ZMQ. So on the other hand, I have the Bluetooth controller that's, well, in this case, a Nintendo Switch controller, and I monitor the input, and then I publish the clicked buttons, and again on ZMQ, and we can read the data in the main loop. The motor driver also provides the current rotational angular velocity of the wheels, which I use to calculate the forward velocity of the robot. And then once we have all of this data, the main loop finally outputs the right motor speed and left motor speed to the driver, and then the driver sets these to the robot itself. So this is done 50 times a second in the policy. So here is the main program for the sim-to-real transfer. First we have this IMU receiver class, and all it does is get the latest IMU data, and that's all it does. It uses the ZMQ library to listen to this IMU stream topic, and then simply read the data and then pass it on to well, just read it and then return as the accelerations and the gyroscope rotations here. Similarly, we have the controller receiver class. It listens to this topic for controller inputs, and that's basically all it does. And when it receives a controller command, it returns a value which looks like this, depending on which controller was which button was clicked. And here is the main program for running the policy. Right, so this alpha is the alpha of the complementary filter for calculating the pitch angle of the robot. Here we have the wheel radius for calculating the forward velocity. Here is the action scale. Now if we look at the Isaac Sim training, I've used the action scale to, I've set the action scale to 6.28 or 2 pi. The motor uses degrees, so I've set this to 360 degrees. So this is multiplying the output of the policy. I have these two objects that use to read the IMU data and the controller data. Here we have the two motor drivers. I'm using a baud rate of 2 million, and this one is the important fine-tuning that we need. So this is the damping value So in the simulation, I've set the damping value to 1, but on the real motor, I've set this to 4. Yeah, so this one you really have to just play around until you get a good value. Why this is not a 1? Well, it's not a 1 because the motor uses a different units, so it uses degrees instead of radians that ISXM uses, so they're not actually going to be the same. But even then, you still have to tune this until you have a value that the robot actually, well, the policy that actually works. Okay, so let's take a look at the main loop. So here is our main loop. When the main loop starts, we get the latest controller data, controller input, and then convert that into velocity command. So if I want to go forward, backward, or rotate, I can set that using this get command, motion command program here. And all it does is, well, look at which button was clicked and then set that corresponding command value to the, well, forward velocity or angular velocity that I wanted to set. The next one is getting the motor status. So when I run these get motor status, it returns the most important data for me, which is the angular velocity in degrees per second for the left and right motors. And these are used to calculate the forward speed. So if you in the simulation, I've used the wheel radius times the sum of the left and right velocities, and it's exactly the same calculation done here to get the forward velocity. And here I'm getting the IMU features, so I get the raw IMU data, and then this is actually exactly the same as the simulation calculation. So basically I'm using a complementary filter to calculate the current pitch angle of the robot. Yes, so joint velocity is calculated from the current angular velocities of the robot, which I got from here, and then I concatenate all of my vectors, and this has to be exactly the same as the simulation. So if I go back to the simulation observations here, it goes IMU pitch angle and angular velocity, then forward velocity, action, joint velocity, and velocity commands, and it's exactly the same in this case, and then you concatenate. And then we just put that observation into my policy here, and out comes the action. And I've decided to apply a little bit of smoothing to the action, because if the robot is perfectly balanced and the robot the policy requests highly accelerated actions, then I kind of wanted to smooth it. That was the idea, but this is controlled by this beta parameter, and I've actually set this to 1. So basically there is actually no smoothing. The actions are being applied directly to the motors in this case. One thing I am doing is clipping the action on a scale of -1 to 2. Now, something interesting with RSL, the algorithm I use for the PPO implementation, is let's see here. I'm setting the joint velocity action with a scale of 6.28. Now, what I'm thinking is the policy is the final layer of the policy is a tanh activation. So it was assumed that the policy outputs -1 to 1, but in reality the output of the policy is linear, so it can actually go from -infinity to infinity. So to deal with the robot trying to spin out of control, I've set an action clipping of -2 to 2. So what this means is when the robot is very close to tipping over, then it can't actually use too much velocity, and it will likely make it less balancing. In any case, the output, so this is the action of the policy, and then I apply it as a set velocity to the motor, and then we finally sleep for the remainder of the duration. So this policy is supposed to run at 50 Hertz, and it will fire off a warning if I go over budget. So let's take a look at how these parts come together. First I run the IMU publisher program, and when I run this, here we are publishing the IMU data at 400 Hertz and exponential smoothing factor of 0.55. And so here we see the XYZ acceleration, where most of it, as you can see, is gravity, which is pointing downwards. And currently the robot is stable, so we don't really see any angular rotation here. And we also have the controller publisher here. And if I click on my controller buttons, then you can see the controller published values changing like this. So these are being used to get the controller commands. And finally we have the main program, which runs the policy on policy loop like this. Now the Jetson Xavier, it's supposed to have well, it's a mini PC, and it's supposed to be a low power device. So I didn't really realize how low that actually means, and it turns out it's quite slow. So you can see here, these warnings are sometimes, so right now you can't really see it, but the robot is balancing by itself and the main loop is running, and occasionally you'll see that this delay says it's higher than 20 milliseconds. Now what that means is the robot actually has a, let me stop this. So the robot has, the policy has a 20 millisecond time window that we have to run, and it occasionally goes over the budget, and in fact it does it more if we run it on the GPU, it turns out. So the problem with the GPU is that when I run it on the GPU, we have to set some well, the observation vector onto the GPU memory, and that actually adds an extra 3 milliseconds, and so we get over budget quite a lot. So currently the policy is actually running on CPU instead of the GPU, which even then is still too close to the 20 millisecond time budget that we have. So let's go over a couple of lessons learned from this project. One was the calibration of IMU. Turns out IMUs have bias and gyroscope bias and gravity vector bias, so calibration turns out to be a pretty important step. Thankfully, Gemini, the coding assistant that I used in this project, is quite good at generating code for calibration, so it kind of went smoothly. The second problem I had was running on GPU versus CPU. Turns out when I run on GPU, it actually goes over budget, time budget, much more than running on CPU. So for a small policy model, it seems to be actually better to run on a CPU. And finally, and this turned out to be my biggest problem for this project, is my two motors are RS485 based controller based motors. What that means is I have to send a message to the motor, and then I have to wait for its response to get data. So here is how much time each part of the well, time budget is how it's being used. So getting the IMU data is basically 0.5 milliseconds. ZMQ is very fast. It's almost instantaneous, so I can get the IMU data very quickly by using ZMQ. but the problem is with getting the current angular velocity. So to get the current angular velocity, I have to send a request to the motor, and that message has to get to the motor controller on the motor itself, and then that needs to respond. And even with 2 million baud rate, the maximum, well, the time required is about 5 milliseconds for 2 motors. And that is quite a lot of time that's being wasted on getting the angular velocity data. Getting the observation vector is also quite slow. It turns out if you use torch and then you calculate data, well, use torch functions and then setting the data onto GPU, it's very slow, and that takes about 5 milliseconds. And finally, forward pass takes about 2 milliseconds, and then set motor speed takes about 5 milliseconds. So once they get the action, I set the velocity onto the motor, and that takes about 5 milliseconds for both motors. So that in total, that means I'm about 17 to 18 milliseconds off my 20 millisecond budget, which seems okay, but it turns out it's not. The reason is, by the time I set the motor speed, or rather when I forward pass, all of my data is almost one full cycle slow. So basically, whenever I forward pass on the policy, the data that I used to calculate the action for the next step is already about 1 step late, or about 20 milliseconds late. And it turns out that for a pendulum robot, if you miss about 2 or 3, or rather if you're late by about 50 milliseconds, then the robot will not be able to be stable. It's just going to oscillate out of control and then fall over. So the biggest problem in this project turned out that I'm using a motor with RS485 communication. And instead, the recommendation is to use CAN-based motors, and these motors have broadcast mode. So basically, the motor is publishing its current status non-stop, and I think you can get down to about 2 milliseconds, and actually less than 2 milliseconds, because it turns out that the USB has a polling rate of 1 millisecond. So basically, whenever you are using a USB-based adapter, then you actually waste an extra 1 millisecond just because of the polling rate of a USB device. So the Jetson Nano has direct CAN pins. So basically, the recommendation is don't use RS485. So some things I did try and didn't work. One is I used delayed action for training in Isaac Lab, and that did not work. So basically, I tried to simulate being 1 step late by calculating an action and then applying it on the next physics time step, and that actually made things worse, so it didn't work. I also tried delaying the motor data, like in the actual case. So I would collect the motor data and then I would apply it for the next training step, and that also made it worse. I also tried training with higher and lower motor damping, and it really didn't make much of a difference. So just tuning the PID parameter on the motor was enough, instead of tuning the damping value in simulation. Okay, so that's it for this video. I think it got a little long, but I hope you learned a few things from this, and in my next video, well, we'll see what I get to in my next video. Okay, thank you very much.